Namaste everyone. This is Dr. Ayesha Butalia. Today we are going to talk about a different approach to solve the problems of data mining and machine learning called as rough set theory. So we are going to use this rough set theory as a framework to design the algorithms for data mining and machine learning. This theory is a mathematical approach to imperfect knowledge, that is, to vagueness or imprecision in the data. Okay, so basically, we are going to talk about the artificial intelligence data, where you can also combine to soft computing techniques where the results or the outcome may not be exact. Okay, if it is 2 plus 2 is equal to 4, that's a hard computing solution, right? Where you have an exact solution to a problem. But at times, there are approximate results, and maybe the outcome may be one or two, or maybe three or four options, depending upon the problem statement. An example, easy example I can give you is that if you are making a machine learning algorithm for automated driving system, and you have got a red signal where you have to stop your car before the uh, red line. Okay, so you need to decide where your car would fit in without crashing the other vehicles and it could accommodate. Now, there can be two to three options. Okay, so you would have two to three options suitable where your car could fit in. Then you would decide which be the best solution. Maybe where you're right now, which is the nearest place where you can go in. Okay, or maybe as a cognitive science and intelligent, you will think that if there is a place where if you fit in, then probably that space may not be used by other person and the space would maybe wasted. So you would go on another option which would be the optimal solution for your problem. So where the solution is not exact, okay, so there can be not one solution for this problem, there can be a number, okay, and another is even imperfect. So sometimes you don't have an exact solution, you have a solution to the approximation. There are at times where there is ambiguity to the data. So let's start. What are the issues of the real world? We have got very large data sets. That's why we are using this framework for data mining. Mixed type of data, there's another questions which come arise. So you need to handle different algorithms for different types of data. For example, text mining, image mining, maybe animation, videos. So different type of algorithms need to be designed for different types of data. There is uncertainty in your problem. For example, if you design an AC, right? So for India, the temperature 25 may be on the auto mode, okay? But in the places where it's too cold, maybe in minus, so auto mode would be something else. So the auto mode of an AC would depend upon the region. So it's uncertain. You can't just feed an exact solution that auto mode is equal to 25, right? Incompleteness in the data. There at times there are missing values in your data sets. So that's incompleteness. You need to handle that also. That's one of the issue. Then data change. Data keep on changing as per your environment. Okay, in our present status, the people who were going very well in certain terms in the lockdown, before the lockdown and the COVID-19 problem, have suddenly got down into crisis. So there are environmental changes, there are business changes which keep on changing, and that also changes your data. And obviously, if data changes, you have a change in your outcome. So you need to basically use the background knowledge at times, okay, to solve this uncertainty issues, whatever we have discussed. Okay, so the use of background knowledge will definitely help us to solve the uncertainty. So as far as the knowledge data discovery KDD is concerned, the soft techniques are distributed as the logic programming, the set theory, and the probability approach. Okay, so if you consider about the logic of the particular system, you can use the deduction algorithms, induction algorithms, and abduction algorithms. Okay, we have got a separate lecture on these, but in general, specifying to this topic, these are the three techniques which you can use for the logic programming. If you come to the probabilistic theory, you can use the stock precision, belief networks, connection networks, and Gaussian decision tree. So for decision tree, we have also discussed a lot of times. Trees help us to decide whether yes or no. Even you can have a fuzzy decision tree that is more approachable to Gaussian networks, okay, where you have weights assigned to a particular node. Okay, so the weights can be from 0 to 1. So the weight can be 0 0.1, 0 0.2, 0 0.3. So not exactly saying as hard computing that your value would be either 0, that is no, for example, or 1, that is yes. You can have approximation values. So that is why we are terming this as a Gaussian tree. So for probabilistic approach, okay, even for soft computing, you can use these type of techniques. Coming to the set theory. Okay, set is a connection of the related data, okay, into one sets. That is also termed as in cluster algorithms, where classification then turned into specialized clusters having similar group of data. So that is basically your sets. So for handling the set theory, you have very good soft computing approach, rough set theory and fuzzy set theory. Okay, we have got some couple of papers. You can go on and see rough fuzzy approach by Ayesha Butalia, some sentiment analysis decision making model I've designed and projected in those papers using the combination of both, because rough set theory is very good to handle uncertainty of data, whereas fuzzy logic is very good in handling the imprecision of data. So as we discussed in our previous issues, that there is uncertainty also, and there is uh, imprecision also, right? So to handle both of them, the combination of rough fuzzy goes very well. That has been described in those papers. I would request that kindly go through those papers. We'll get a lot of mathematical approach using these through techniques. Now concentrating on the rough sets. So as discussed now, soft computing versus hard computing. So obviously rough sets would be used for hard computing, but going on to the issues related to the real issues related to soft computing, this would be very good approach. Then again, in terms of machine learning versus data mining. So data mining are large sets. Rough set theory is a very good approach to handle large sets, to take out knowledge from your data, large data sets through your data mining algorithms. We will see that. And even for designing a new algorithm to having a new knowledge database uh, using the existing machine learning algorithms. Now, same algorithms of data mining, you can use it for machine learning as well. The only difference is when the data set is small, the same algorithm is used for machine learning, otherwise it is data mining. In our previous lectures, we had discussed about the descriptive model approach, where you can use rough set theory for machine learning. And if you use rough set theory as a predictive modeling approach, then basically it will act as a framework for data mining. So rough set theory was developed by Z. Pollock, okay, in early 1980s. So it's not something new, but yes, I've seen that this theory has been used by very less people, probably because of the unawareness of its potential. So the main goals of rough set analysis is induction of approximation of sets. So as said that it is a powerful tool to handle uncertainty issues, right? So uncertainty will have a lot of approximations, lot of approximate values. Okay, so it will be handling that. It constitutes of a sound basis of knowledge data discovery. It's a mathematical tool to discover patterns hidden in the data. So as in our previous lectures, we always discuss that whether it is data mining, machine learning, soft computing, AI, everything, actually what you are doing primarily is to extract patterns. And through that patterns, then you design an algorithm, feed into your system, depending upon your approach. So it can be used for feature selection, feature extraction, data reduction, decision rule generation, and pattern extraction in the form of templates and association rules. We have discussed this association rules in details in our predictive approach using data mining. Now, basically, feature selection, feature extraction, data reduction, they're all the same. What we are trying to do is, if there are existing attributes, okay, attributes, you can consider the columns of the table. If there are, suppose, n number of attributes, the designing of that decision system would be more complex. So if we try to remove the redundancy by lessening the number of our attributes, obviously the complexity of the system will decrease. So that is nothing but feature selection or feature extraction of data reduction. So if suppose there are, say, 20 attributes, if we select 4 attributes which are related to our problem statement, we are trying to extract the features. Okay, so automatically what we are doing, we are reducing from 20 attributes to 4 attributes. So hence, feature extraction, feature selection, or feature reduction, or data reduction, they all are interrelated. So these extensions of RST, it helps to develop new methods for the decomposition of large data sets. So in distributed and multi-agent systems, basically rough set theory is a very powerful tool to handle feature reduction. There's one of my paper on mushroom analysis, where a farmer tries to pluck the mushroom plant, and there are 2 categories of mushroom: edible and poisonous. So there are certain attributes, there are 16 attributes which decide whether the plant is audible or edible or poisonous, as per our data sets used from our UCR repository. Okay, it's a machine learning site. The exact samples and their values are given for the student research. After using the rough set theory, I had proposed the algorithm that from 16 attributes, it reduced to 3 attributes. So now, remembering 16 attributes was a tough job for a farmer. Remembering 3 classifier attributes to decide whether to pluck the plant using its edible characteristics, or to ignore it using a poisonous, right? 3 attributes we tried to reduce, and it was very useful for the farmers to decide that. So you can, a humble request, you can also go through that paper. You can just type Ayesha Butalia feature reduction through rough set theory, you will get it. IEEE transaction paper. So the basic concepts of rough set theory is the decision table or the information system. In our DBMS or the data mining, we call it as tables. Okay, so relational database system, we can use it very easily, because that's the most handy type of database system in comparison to the hierarchical model or network model using pointers, etc. Next topic is the indiscernibility, where we are trying to reduce the number of attributes, or you are trying to extract the indiscernible objects, that is the important objects, okay, and remove the discernible ones. Then next is the set approximation, where you have a lower approximation, upper approximation. We will see that in detail. Redux and core, rough membership, dependency of attributes, decision rule, future scope, and references. I'll try to summarize this in this lecture, but maybe if not covered, I'll try to explain all these terms in probably 2 to 3 lectures. So kindly go through that. So information system or decision table, okay, it's a composed of 4 tuples. So tuples, the attributes, or this is the name of the database, and these are the attributes. So U is a closed universe, finite set of n objects, say x1 to xn. So it's a non-empty set, basically consisting of objects. Then V is the domain values of that attributes Q, right? So if there are Q attributes, V will consist of the domain values. If suppose one of the attribute is percentage, the domain value of percentage is 1 to 100, right? So similarly, every object and the attributes will have some domain range that would be specified by the set V. Okay, obviously, if there are Q attributes, there will be Q objects defining the domain values, right? Q is the number of attributes, V is that is the set of the attributes, V is the domain values of that Q, and F is the total decision function called as the information function, such that F of X of Q belongs to V of Q for every X belongs to Q, and Q belongs to Q. That means that function should be satisfying the domain values. Okay, it should not violate the domain values. Such type of functions on that attributes and the objects we need to define. For example, if you are using an object oriented language, so you have classes. Okay, classes have got members and member functions, and then classes, when you define the objects of each class. So obviously when you define the object of each class, every object again will have its attributes and its functions. So it's something like that, right? So this is the entire class. This is the number of objects of that class. This is the number of attributes or the member data of that class. This is the domain of that attributes, and these are the member functions of that class. So in terms of class, we are mentioning it as an information system here in terms of rough set theory. Okay, U as the number of objects, Q as the number of attribute set, V as the number of the range of domain values, and F is the functions. Now taking this with an example, U, the number of objects here are 8. How we are saying it as 8 over here? Because if you see this table, there are 8 objects, right? X1 to X8. Then Q, the number of attributes. Okay, so we have Q1, Q2, Q3. This is Q1 attribute, this is Q2 attribute, and this is Q3 attribute. That is engine, size, and color respectively. It's given here. Then now defining the range of each attribute. So now we will consider the first attribute, engine. Okay, so what are the domain? Here you can see the domain is propane, diesel, and gasoline. That is, these are the values given in the table. Similarly, the other attribute is size. So what is the domain? Compact, medium, and full. No other values apart from these three are there, right? Then for color, it is black, white, red, gold, and silver. You can see here black, white, red, gold, and silver. No other values apart from this. And for decision, now this is the decision attribute. These are the condition attributes, right? This is the number of objects, like serial numbers also. So these are the condition attributes. Based on the condition attributes, the decision outcome is maintained. Okay, so this is a survey taken of a car system, where if the car is having engine propane, the object of the car as car. Okay, if the car has engine propane, size as compact, color as black, then we decide that this car is a good. If it has diesel and then size is medium, color is gold, the feedback is bad. Okay, so similarly we have got. Now, so decision values domain is, now V is the domain, right? So the decision value domain is either it is good or bad. And then this, this we can decide for our own problem statement. Okay, looking at this example, we can decide the objects, we can decide our condition attributes, and what should be the decision. It can be, say, in the form of yes or no. It can be in the form of 0, 1, anything. Okay. So these the decision variables, and C is the condition variables. Now coming to the issues in the decision table, the same or the indiscernible objects may be represented several times, right? So there can be repetition of data. Some of the attributes may be superfluous, that is redundant. Okay, that is the removal, worsen the classification. So what is the solution? M of Q. Okay, M of Q, basically you can consider it that in DBMS there are a lot of normalization forms, 1NF, 2NF, 3NF, 4NF. So you can convert it into at least till 3NF, so that all these issues in the decision table are solved. For example, if you see 1NF, we have got a separate lecture on all the normalization. You can go to our YouTube channel. But just to say here, 1NF means that if the same thing is repeated, okay, for another object, say X9, so repetition will definitely increase the complexity. Ultimately, we have come to know that if these three conditions are true, the decision attribute is good. So we need not have another object for the same thing, right? So we can remove that redundancy. So this is called as 1NF. Similarly, 2NF, 3NF, and you try to remove your redundancy and indiscernible handling through your normalization form, so that you now have the S on which you can work further. So what is this indiscernible relation? Right, so this x of a, x is the object of the attribute q. Okay, so it splits the given universe u into a family of equivalence class x1 to xr. So if you can see here in this example, this is u, right? The number of objects, and these are what? The specified objects. So this is the included in the indivisible sets. So here x1 to xr. So in our previous example, it is x1 to x8, right? And then we call the objects x and y are indivisible by the set of attributes A in S denoted by x, A bar, y, right? Now, what is the actual meaning of indiscernible? Indiscernible means that the things which are not exactly clear. Now, here, if you can see in our example, whenever there is a propane, now there is no other propane over here, so we can say that whenever the engine is propane, okay, the car is good. Here if you see diesel, whenever the engine is diesel, always you see that it is bad, right? But in terms of gasoline, sometimes if the engine is gasoline, then it is good. In some cases, if it is gasoline, then this is bad, right? So here the example clearly shows that there is uncertainty whenever the engine is gasoline. So you need to consider the other uh, condition attributes also, and that is called as indiscernible relations. So in this particular figure, these four objects are included in the indiscernible relation. But how to take it mathematically? It denotes an A elementary set as equivalence classes, including an object S. The elementary set Xi are the blocks of the partition of Q and represent the smallest discernible objects, group of objects. They are called as A basic knowledge. So discernibility of A on X. So this object X. Now X, if we consider here as X5, if in terms, so A would be engine, then another A would be, another set would be size, another set would be color. So if we consider this A on X, A comma B, the function X comma A is equal to B, where the domain values should belong to X and A belongs to A. So in this particular mathematical formula, if you try to evaluate, always the value would be B if you consider these objects and the A is engine. But if you consider gasoline as your X, then sometimes your A would be good and sometimes it will be bad, right? So here is the example. Equivalence classes are the, you can classify in terms of engine, you can classify in terms of size, you can classify in terms of color, you can also classify in terms of engine and size only, you can also classify in terms of size and color only, or you can classify in terms of engine, color and size. But since here the example is given that the condition attributes are 3, the best disability relationship would be to include all the condition attributes. But this is what we are seeing the example. If there are large data sets and we are database designers, we are data mining designers, we are machine learning algorithm expert, then we have to decide out of 25 attributes which are the discernible objects. So here let's have a look. See, x1 object of A. Okay, here A is engine only. Just kindly note. So it is x1, right? X1 because if engine is only propane. Then x2 of A is equal to x3 of A. Obviously, this is equal to this and also this. That is why x2, x3 and x4 are same. So they become one equivalence class only in terms of engine, right? Then x5 of A, that is this, this and this. These all four are same if you take only engine. Then we have another equivalence class x5, x6, x7 and x8. So the equivalence classes are now x1 is equal to small x1, okay, because this is propane. Capital X2 is this, which is related to diesel, and X3 are all the objects which are related to gasoline. Now, what is indivisible relation on engine? What you do, you just combine all the equivalence classes. So how it will be? X1 then this set, and then this set. Okay. Similarly, you can calculate the equivalence classes in terms of engine and size. You can similarly calculate equivalence classes on size and color. You can calculate on engine and color, and you can also calculate on engine size and color. Combine it, and then you can propose the disciple relation on engine size and color. What will be the objects categories? So what are the observations from these equivalence classes? Why actually we did it all these? An equivalence relation reduces a partitioning of the universe. So we actually did it to partition it, right? So set theory is what? Basically in our previous lectures, previous slides, we just saw that this technique is for set theory. So we have now sets, right? So these equivalence classes are nothing but the sets. We had 3 sets in terms of engine. Okay, so that is nothing but the partitions. So partitions can build new subsets of the universe. By partitioning, you get another type of knowledge. Okay, you try to extract that, yes, if the propane engine is there, we have no ambiguity. If diesel engine is there, we have no ambiguity. But when it comes to gasoline engine, we have got ambiguity. So here, there is an imprecision in the data. There is uncertainty in the data. Let's handle it in a different way. So subsets that are more often most of interest have same value of decision attribute. It may happen, however, that a concept such as a good engine for a car cannot be defined in a crisp manner. Why we cannot define it? Because we already saw in certain conditions gasoline was saying it is a good car, in another condition it was saying it a bad car. So it cannot be defined in a crisp manner. Crisp manner means hard computing. Okay, the answer is not crisp, yes or no. It is ambiguity. It may be or it may not be. So whenever you have answers like may be, then that is called as soft computing techniques and uncertainty and imprecision issues. Now coming to the set approximation. Now this is A. This is having a bar at the downside. So this is called as lower approximation on the equivalence class X, right? So what is that? On the universe of objects, Y should belong to A star. A star is all the indisciplinary relations. Okay, so it should belong to the Y and X, both the objects. Okay, so indisciplinary A approximation reason of a concept X in the lower approximation of the entire system, the objects certainly belong to the concept X. And this is upper approximation. The upper approximation, the object certainly or may be belonging to the concept X. So if you see our previous example, lower approximation sets would be which are giving us exact results, like that is propane and diesel. But upper approximate set would give us gasoline, where the answer can be may be, right? So the boundary region is what? It is the doubtful region. So doubtful region, how to calculate the boundary region? You just subtract lower approximation from the upper approximation, and that is called the boundary region, right? So if the lower approximation is also called the A positive region, okay, positive region of A in terms of X equivalence class, right? In your subsystem S or your information system or your decision table. The boundary region, okay, it is denoted as Bn, okay, A of X in S. And what is U minus A of X? This is nothing but the negative region. So negative region and upper approximation region, sometimes people think that they are the same, okay, but it may not always tally. So the upper approximation is different, lower approximation is different, the boundary region is different, negative region is different. But yes, positive region is the same as that of the lower approximation. Now this is more clear, okay, when you see the example. And this is just a diagrammatical representation, right? So this is the entire S, which is in blue, and it has got grids. That means it has got attributes and rows, that is called as granules of knowledge, and the set of objects. Okay, now these are the upper approximation. That means the ambiguity is there in this upper approximation. Answer can be yes or no. Okay, and the denoted ring is the set. and the lower approximation is this region. Now what is seen here clearly, that the lower approximation is totally inside the set. That means the answer is quite positive. It is the definite answer, either yes or no. But the upper region is outside the set. It may be, that means it is a part of lower approximation. So it is clearly seen here that all the members of lower approximation will also be the members of the uh, upper approximation, and this is the boundary, right? This is the boundary. Now let's see with the same example how to calculate the upper approximation and lower approximation. So here x1 is equivalence class capital X1 having object x1, x5 and x6. If you see x1, x5 and x6. Okay, why we have selected these three attributes? Because in these three objects the decision is good, right? So if D is equal to good and A is equal to engine, okay, so the approximation set, now here A is the attribute, on engine we are calculating the lower approximation, and X is the equivalence class, that is these are the groupings on which value where D is equal to good, right? So these are the groupings, and how to calculate the lower approximation, this is equal to X. Why? Because if this is the value propane, then definitely the answer is good. But if you consider x5 and x6, okay, and if you see all the other attributes related to gasoline, the answer is not always good. So that means the x5 and x6, they got deducted, right? So lower approximation, as we said, it's a positive region. The answer is always yes. Whereas in gasoline, the answer was also bad. That means it was in the maybe part. So that's why it will go in the upper approximation. So here, upper approximation is equal to x1 union x2. Now this is a typing mistake here. It should be x2, and x2 is actually all the attributes related to gasoline, right? So if you take the gasoline, that is x5, s6, x7 and x8. So you have to do the union. Okay, so you will get x1, x5, x6, x7 and x8. If we calculate the boundary region, then it is upper approximation minus lower approximation. So this is the boundary region. Why x1 is not here? Because x1 is actually this part. Okay, that means the answer is totally yes when it comes to propane, right? Whereas if it comes to gasoline, okay, it may be. So that is why this is the yellow region, right? So yellow region is totally your x1 also, and your x5, x6, x7, x8. Whereas the boundary region is not including the x1. Apart from that, it will be x5, x6, x7 and x8. And then what is the negative region? U minus upper approximation. So it will be U is what? All the objects, and minus the upper approximation. So upper approximation is all these attributes. So what are remaining is the x2, x3 and x4. So if you consider the diesel type of attributes. So the class decision class good is rough, since the boundary region is not empty. Whenever the boundary region is not empty, such a problem is called rough. The moment we say rough, that means there are certain values in your information system where the outcomes may be are in the terms of maybe. That means either yes or no. That means indefinite answers. So such type of attributes need to be specially handled by whatever we are going to see the algorithms of rough set theory. We have to handle it because we have identified that this data is rough. Okay. So these are the negative attributes. So if you see here with the help of the diagram, this is yes, no ambiguity when it comes to propane. When it comes to gasoline, you have yes and no. And whenever it comes to diesel, then the answer is absolutely no. Okay. So this is the upper approximation, this is the negative region, and this is the lower approximation or the positive region. This is the boundary region. So 4 basic classes of rough set. A set X is roughly A definable if lower approximation is not equal to 0 and upper approximation is not equal to universe. Elements, whether they belong to X or minus X, can be decided. Another class category is if a set is externally A non-definable, if in S, A lower approximation is not equal to 0 and upper approximation is equal to U. Then there will be a reverse case of this, and then there will be a reverse case of this. So there can be 4 categories depending upon the lower approximation and the upper approximation types of set. If everything is in the maybe form, okay, for example, if the upper universe becomes U, that means everything is ambiguity. So the entire database is totally rough, okay. Whereas over here, if this is not equal to 0, that means some part is not rough, it is crisp. Because if lower approximation has some values, that means some part we can say that exactly this is going to be the result. For example, in our previous example, propane was totally crisp. Okay, there was no ambiguity related to propane. Even there was no ambiguity related to diesel. The ambiguity was only related to the gasoline, and that is your upper approximation, right? So how to calculate the accuracy of approximation? It is by this term, denoted by this alpha, okay, on the attribute A and the equivalence class X. So cardinality of lower approximation upon cardinality of upper approximation. Cardinality denotes this denotes the cardinality. Cardinality means you have to calculate the numbers, okay, the number of objects in that set. So obviously, the cardinality is going to be in between 0, less than or equal to 1. Okay, so it will be in between 0 and 1, and it can be 0 and 1 also. If it is 0 or it is 1, then it is a crisp type of cardinality. So if cardinality is equal to 1, then X is crisp with respect to A. And if it is less than 1, then it is rough with respect to A. Okay, this is all what we discussed. So we'll stop here. In our next lecture, we will be discussing about the dispensable and indispensable attributes, because once we decide what are important and unimportant attributes, then only we can have a feature reduction algorithm. Okay, so we will be discussing how to incorporate rough set theory for feature selection and feature reduction. Okay, so thank you very much for your patience listening. I hope this lecture on rough set theory might be useful to you. If you have any questions, you can post on the comment box or you mail me on the group. Thank you.